Hi students, hope you all are doing good. As you know, today we have to discuss the topic electrostatic pressure, a very interesting topic. And today is the last session for the module 8, electric potential and potential energy. Okay, capacitance we will be starting from next class. Before I discuss the concept of electrostatic pressure, some few important and conceptual questions I will be discussing today, and it will be like a revision of whatever we have done till now. So I hope all of you will find it useful. So please see it carefully. So imagine there is electric field in this direction. Okay, uniform electric field, and I take 2 points in this electric field, point A and point B, separated by some distance d, let's say. Okay, so now when I move in the direction of electric field, potential should decrease, right? You remember electric field is from higher potential to lower potential. So if you want to know the potential difference in magnitude, then it will be equals to this electric field times this d. No need to write cos theta here because d is in this direction, electric field is also in the same direction. So cos theta will be 1. So this formula I want all of you to remember, very important simple problem, simple formula, but only it is only used when E is uniform, is constant. If E is given as some function of position, okay, then to find the potential difference, you have to integrate E dx. Okay, so basically you have to find potential difference. See, if this is potential difference separated by d distance, right? What is this? Potential difference between A and B separated by d distance, right? So what will be this? Potential difference between 2 points separated by dx distance. Then if you integrate, you will get the total potential difference. So this is small potential difference. If you integrate, you will get total potential difference. For example, if E was constant, what you can do? You can take E outside. Then integration of dx, 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 if you add, you will get the total distance, which I have written d. So if E was constant, you can take it out, then you will get d, which is nothing but distance between the 2 points in the electric field. So please remember, in order to have potential difference, there has to be electric field, right? So this delta V actually means VA minus VB. Okay, so keep these formulas in your mind. Then the next concept that I want to revise with all of you is the concept of potential energy. Okay, so if there is, let's say, electric field, again, let us say there is electric field, then at every point, as I told, there will be some potential at every point. What does it mean? Definition you should know. So definition of potential is what? Work done to bring 1 coulomb charge, or you can say unit charge, from infinity to this point. So that is the meaning of potential. So potential is work done to bring 1 coulomb charge, or you can say unit charge, from infinity to that point P, let's say, if you want potential at P. Okay students, now instead of bringing unit charge, if I bring Q charge from infinity to this point, then work done will be what? This is work done to bring 1 coulomb charge. So work done to bring Q coulomb charge will be Q into V. From where to where? From infinity to that point. So that is your potential energy at that point. So this is potential energy of this charge when it is at this point. Understood? So it has to be under some electric field, right? So when I say this pen has potential energy, there is earth below, right, which is applying force. So similarly, when I put this charge here, I am saying it has potential energy because there is a force acting on it, which is due to the electric field. So whoever has brought this charge from infinity to this point has to do work against this electric field. Okay. So we have used, if you remember, so many problems where we used L comma. L comma means law of conservation of mechanical energy. There we have used this formula because we know potential due to different source charge. So if you put any charge Q at a point, then you can easily find potential energy by multiplying the charge with the potential. Please remember, this Q here represents the charge which you are moving from infinity to that point, and this V will be produced by some source charge, right? By some source charge. For example, when I say there is electric field, obviously there is some source charge somewhere. It could be ring of charge, it could be line of charge, it could be sheet of charge. We know spherical charge, it can be shell of charge, it can be. So we know formula for electric field due to different kinds of charge distribution. So please keep this formula also in mind. Then I told you, if you want to move the charge not from infinity to some point, but let us say you are moving the charge from one point to another point. So this is electric field again. This is point A, this is point B. And this electric field is again, remember, due to some source charge. Now if you move another charge from this point to this point, Q charge, then work done to move this Q charge from A to B. What was the formula? Q into VB minus VA. That is because work done this is work done by some external agency. It could be Pankaj sir also, right? So if you remember what I used to tell you, work done by external force from A to B will be change in potential energy. Change in potential energy means UB minus UA. And UB is what? Just now I told, Q into VB minus Q into VA. Then you take Q common, you will get this. So this is work done by external force to move this charge from point A to point B slowly, I told. And if you want work done by not external force but electric field from A to B, then what I told, it is minus of this work done. Matlab, it is minus of change in potential energy. So all these concepts please try to remember. Now let me ask you a very interesting and simple question based on all this. So try to answer, okay? So imagine the question is like this. This is x-axis and this is the origin, let's say x equal to 0, and this is point x equal to 2 meter, x equals to 4 meter, 6 meter, like that. And I'm saying to you that at these different points potential is changing like this: 0 volt, 10 volt, 20 volt, 30 volt, like this. So now if I ask, what is the electric field? What is the electric field? Let me give you options. First option, 5 volt per meter. Second option, equal to or greater than 5 volt per meter. Third option, equal to or less than 5 volt per meter. Option D, none of this. So pause the video and try to solve. Now if you have solved, most of you may think this is the answer. Now you will think, the reason why this is the answer, you will think, sir, just now you told potential difference between 2 points is equals to E into D, right? And potential difference, if you calculate between these 2 points or between these 2 points, your wish. So between these 2 points, what is the potential difference? 10 minus 0. Electric field we have to find. What is this distance? 2. So from here you will get E is equals to 5 volt per meter. So you may think this is the right answer. However, students, you have to be careful. I have not told you in this question electric field is along x-axis. If electric field was along x-axis, then this would be the answer. Electric field could be this way also, right? Yes or no? I just gave you potential of these points. Okay. So now you see, if I give you potential of these points, then let us say these are your equipotential surfaces. Let us assume these are your equipotential surfaces. If these are your equipotential surfaces, then all this will be 0 volt, all this will be 10 volt, all this will be 20 volt, all this will be 30 volt. Okay, so in that case, no doubt electric field will be perpendicular. You know that electric field lines are perpendicular to equipotential surfaces. I hope you remember that property, right? So in that case, you can see electric field is here. This distance is also in the same direction. Then you can use this formula and the answer will be like this, no doubt. However, it is not compulsory that equipotential surfaces should be like this, right? In order for the field to be uniform. If this was the case, then your answer is correct. But suppose it was like this. This is x-axis, this is 0, 2 meter, 4 meter, 6 meter, so on, and this is 0 volt, 10 volt, 20 volt, 30 volt. Let us say your equipotential surfaces are like this. In that case, you can see this is also 10 volt everywhere, 10 volt, 10 volt, sorry, 0 volt, 10 volt everywhere, 20 volt, 30 volt, right? But now, where will be electric field? Electric field will be now in this direction. So what you have calculated here is only the x component of electric field. Y component you have not calculated. So when you write this formula, okay, so actually here cos theta is there, no? And from the diagram, since electric field was not mentioned in the question, it could be in any direction. So if electric field is along x-axis, then your D and electric field will be in same direction. Then no need to write cos theta. Then your electric field will be how much? 5 volt per meter. But if electric field is not along x-axis, but if it is at some random angle, then your electric field, then you have to write cos theta here, because this will be E, this will be your D, this is D, na? D. This is your E, and the theta will come. So then your formula, if I use, it will be 10 minus 0 E into 2, same thing, but you have to write now cos theta also. And that, what is the theta? If electric field is not along x-axis, if it is in this direction, then this is your theta, angle between electric field and your displacement. Cos theta was also there, remember. In general, there will be cos theta here. So your electric field will be how much in that case? 10 by 2 will be 5 divided by cos theta. And 5 divides, you know, cos theta is a number either 1 or less than 1. So since this is a number less than 1 or 1, if this is 1, then it will be 5. This is the answer. If this is 1. But otherwise, this will be less than 1. If it is less than 1, like let's say 1 by 2, then 2 will go up. Electric field will be how much? 10. So in general, electric field will be either 5 or greater than 5. Understood, students, now? Because this is greater than 5 volt. Why? Because cos theta is a number less than 1, or it can be 1. If it is 1, then it means you are assuming if cos theta is 1, then what is the meaning of theta? Then it is 0 degree. So if theta is 0 degree, then you are saying electric field is in this direction. So if electric field was along x-axis, then this answer is correct. But that was not mentioned in the question. The only thing I told is electric field is uniform. That's it. But I did not mention the direction. I just mentioned the potential at different coordinates of your x-axis. Okay, students, so be very careful. So the answer was not 5 volt. It is 5 volt, or it can be more than 5 volt. So this is question I have taken from H.C. Verma textbook. Okay. So I hope everybody understood this. Next thing is, so this is the one concept I wanted to revise. Another concept is, look carefully. All these are for entrance only, okay? So suppose I give you a small sphere of charge q1 radius r1, another sphere of charge q2 radius r2. Right now the potential of these two may be same, may not be same. So on the surface, what will be the potential of this sphere? 1 by 4 pi epsilon naught q1. On the surface means you should use the radius, which is r1. And this is 1 by 4 pi epsilon naught q2 by r2. Correct now? Okay. So now let us say I connect a wire between them. Suppose I connect both of them by one wire. Then let us assume V1 is greater than V2. Then charges will flow or not flow? Tell me quickly. Charges will flow now, 100%. So once charges will flow, let us assume delta Q charge will flow. If delta Q charge will flow, now this will have how much charge? Q1 minus delta Q. And this will have how much charge? Q2 plus delta Q. And then how long the charge will flow? Till the potential of this and this are equal. So now what will be the potential on the surface of this? 1 by 4 pi epsilon naught. What is the charge now? Q1 minus delta Q divided by radius. What is the radius? R1. And the potential here should be same as here now. What is the potential here? Same thing. 1 by 4 pi epsilon naught. Charge is now how much? Q2 plus delta Q divided by radius. Radius is R. Then this and this you can cancel, and then you can solve to find delta Q. Okay, in terms of what? In terms of Q1, Q2, R1, R2. Now my question is, do you think the whole charge will go there? Whole charge will go? Will whole Q1 go there? Will it go? Not possible. How it will go? If the whole charge goes there, then potential of this point will be 0. Potential of this point is not 0. So, but I said how long the charge will go? The charge will go till the potentials are same. So please understand, whole charge will not go. Charge will go, some amount of charge will go till they have same potential. And how to find how much charge will go? Make the potentials equal and solve. Okay, for example, let me take a simple case. Suppose it was QQ for simplicity. If I take QQ, then this will be Q, this will be also Q. And let us say this radius is R, this radius is 2R. Okay, just for simplicity, I am making the question little bit simpler. So then you can solve, this will be R, this will be 2R. Right? So then if I solve this easily, what will you get? So R will cancel, cross multiply, 2Q minus 2 delta Q will be equal to Q plus delta Q. Correct na? Cross multiply 2. Then you bring this Q this side, you will get Q, 2Q minus Q, and that side it will become 3 times delta Q. So delta Q will be how much? Q by 3. So how much charge will flow? Q by 3. So after this much charge will flow, then the potentials will be equal. That configuration or that situation is called electrostatic equilibrium. It is like thermal equilibrium. Heat will flow till temperatures will become equal. Here charges will keep flowing till potentials will become equal. Then what will be the new charge if I ask on these two spheres? So it will be Q minus delta Q, Q plus delta Q, because in the question I have given QQ. So what will be the charge on this now? Q minus Q by 3. That will be 2Q by 3. And this will be Q plus Q by 3. Q plus Q by 3. That will be how much? 4Q by 3. So that will be the new charges. So the whole charge will not go. That is the point. Now see something very, very interesting. And why charges are flowing? Charges are flowing so that the potentials are equal. And that is because for a conductor, potential everywhere must be constant, because electric field inside the conductor is 0. Now listen to this carefully. Suppose here there is a charge Q1 and I want this whole charge to go to another conductor, whole charge. Now if you connect it to another conductor here and put a wire, I have told you whole charge will not go. But the beautiful thing which I will prove you later is if you put another concentric bigger conducting shell. Okay, and then if I connect a wire, students, you will be shocked to realize that the whole charge will go to the outer sphere. So after equilibrium, you will see it will look like this when there is a wire connected between them. So this will have zero charge and the whole charge will go outside here. This is how it will be situation after equilibrium. Here charge will be zero. Now you may think why it is. Now without mathematics, if you want to understand without mathematics, then it's very easy. If you remember, I told you charges, like charges, they like each other or they don't like charges, they don't like each other because they repel each other. So before, when this wire was not there, this charge was spreading on the outer surface. That is the maximum far they can be, right, by staying on the outer surface. However, once you give them a conducting path, you give these charges a conducting path, then these charges will think, Arey, why will I stay here when I have option to spread more far? So the option they have to spread more far is on the outer surface of this conductor. Once you join with a wire, this whole thing became one conductor now. Potential everywhere has to be same, remember. So the whole charge will go on the outer surface. Already I have explained this while talking about electrostatics of conductor. So whenever you give charge to a conductor, the charge will spread on the outer surface. So once you connect a wire, this whole charge will flow on the outer surface. Okay. So let us discuss another topic. Suppose this has charge Q1 and this has charge Q2. These are the charges given. Not visible, right? Let me write here. So this has charge Q2 everywhere and this has charge Q1. Now suppose I connect a wire. You will find that after equilibrium, this will be 0 and the whole charge Q1 will go to the outer shell. So total charge on the outer shell will be Q1 plus Q2. So let me now try to prove those who are mathematics lover. They may think, sir, physics explanation is okay, but please try to show using mathematics also. So let me now try to explain to you using mathematics. So look carefully. Proof I am trying to give you. So this is one shell with radius Q1, with charge Q1, another shell charge Q2, let us assume. This has radius small r, this has radius capital R, let's say. Now, let us ask what is the potential of this point A and this point B right now. Okay, you can do another problem where Q2 is not there. That will be more easy, right? Wherever there is Q2 in my derivation, you put 0 if you want to do without Q2. Here, no need to distribute the charge like minus Q1 and Q1 plus Q2, no need, because we want potential. Now look carefully. Who will produce potential at point A? Both the charges, right? So what will be the potential at A due to this shell? 1 by 4 pi epsilon naught charge on the shell, and since this point is on the surface, you have to use radius of the shell, which is smaller. Then this shell will also produce potential at A, right? At any point, potential is produced by all the charges. So this charge will also produce potential at this point. For this charge, where is this point? Inside. And inside, potential is same as on its surface. So 1 by 4 pi epsilon naught, we are calculating due to which charge now? Q2. And the point where I want is inside this charge Q2. Shell of charge, shell. So potential here will be same as on the surface. And on the surface, what do we write? Radius of the shell, which is capital R. What about potential at point B? So at B also, there will be potential due to both the charges. Now, for point B, for this charge, point B is where? Outside. So formula is 1 by 4 pi epsilon naught charge Q1 divided by. If the point is outside, then what is the formula for potential? 1 by 4 pi epsilon naught Q by R, and this small r represents from center to that point. If the point where you want potential is outside, then this is the formula. Please, you have to check the formula, okay? And many times I have revised this. So since point B is outside this shell, potential here due to this shell will be this small, this R you have to use. Now what is that R? Same as capital R. Plus, who will also produce potential at B? Q2 will also produce potential at B, and that will be Q2 divided by R. Why R? Because it is on the surface of this shell. So this is the potential at A due to Q1. This is the potential at A due to Q2. Same thing I have done for B. Now let me ask, what is the potential difference? VA minus VB. So you can see, if you subtract, this will cancel. So you will get 1 by 4 pi epsilon naught. Q1 will be common. 1 by R minus 1 by capital R. Correct? No, this minus this I am doing. Now see, small r is less than capital R, right? But so 1 by small r will be greater than 1 by capital R, right? 2 is less than 3. 1 by 2 is greater than 1 by 3. You all know this. Check, otherwise use calculator. So this ratio is greater than 0. Correct na? So if this charge is positive, then you know this answer will be greater than 0. And you can see this potential difference does not depend on which charge? On Q2 charge. So no matter how much charge is here, it doesn't matter. Potential of this point is always greater than potential of this point because the difference is coming positive. Understood? So no matter what is Q2, this point will be always at higher potential than this point. This is the main part, students, main part. And I am not doing anything. I am just applying the formulas and taking the facts, talking about the facts. So now if you connect a conducting wire between them, which is at higher potential A, so this charge will start flowing this way. As this charge will go this side, this will increase. Yes or no? But even if this increases, you know this difference does not depend on this charge. Understanding? So even if this is increasing, it doesn't matter. This will be always higher potential. Till when? Till the whole charge will go. Once the whole charge will go, then only this Q1 will be 0 now. If whole charge will go, then Q1 will be 0. Then potential of A and B will be equal. If this becomes 0, then what will you get? VA minus VB is 0. That means VA will be equal to VB. So the only way nature will allow potentials to be same in this case, okay, in this case, is if the whole charge will go to the outer shell. Okay, students, so hope everybody understood this. Okay, now we want to talk about electrostatic pressure. But before I talk about electrostatic pressure, let us discuss one more concept. Suppose I give you a sheet of charge, non-conducting, okay, non-conducting. Then what was the formula for electric field at any point? Sorry, non-conducting is not visible, right? Okay. So what was the formula for electric field at any point? Quickly tell me. If this has a surface charge density sigma, which means charge on this surface divided by area of this surface, then what was the formula for electric field? E equals to sigma by 2 epsilon naught. I hope everybody remembers this. Now suppose I give you a conducting sheet, which is again charge. Then what was the electric field just outside? Okay, just outside. This we did in the first chapter. This we did in the second chapter while doing electrostatics of conductor. Can you remind me of the formula? It was sigma by epsilon naught. And the reason why it was like this is because no matter how thin it is, okay, it will have some thickness, remember. It cannot be zero thickness, no. Even if it is like this, it will have some thickness, see. This much thickness will be there. Even if it is just like a paper, it will still have thickness. So if it has thickness, then the reason why it came sigma by epsilon naught in the case of conductor was, if you remember, let me show from this side. So if you see from this side, you will see this part, right? This part, let me show you. Then if you want electric field here, if you remember, we took a Gaussian surface like this because I want just outside. And through this surface, electric flux was E into A. Electric flux, electric field into area. And here, if you remember, inside electric field is 0. Electric field inside the conductor is 0. So there was no electric flux through this surface. So this came equal to charge inside. Charge inside was sigma into area divided by epsilon naught. And that is how I got this formula. One quick revision I have done. And that happens because inside, if it is conducting sheet, and inside the sheet electric field is 0, which is not required in the case of non-conducting sheet. Okay, so here if you remember, I took from this side, if you see, this is how the charges are spread. Okay, and here if I ask electric field, I took a Gaussian surface like this, and electric field was like this, E. So through here flux was E into A, through this surface flux was E into A, and that was equal to charge inside divided by epsilon naught. Charge inside was sigma into A. So from here we got E equal to sigma by 2 epsilon naught. Okay students, so this was in the case of just sheet of charge. Just sheet of charge. So here the thickness can be assumed to be negligible, no problem. But here, even if you say its thickness is very, very small, you can always draw a Gaussian surface in such a way that one surface is inside the conductor and one is outside the conductor. And since electric field here is 0, electric field just outside the conductor, just outside I am talking about, will be sigma by epsilon naught. Now, these formulas you remember. Now let me give you one H.C. Verma question, conceptual question again. And many students do mistake in this. So look carefully. So what they do is this. So the question is very interesting question. Let me write the name of the person also. Otherwise copyright issue may happen, right? So look here, question here. So here I have a sheet of non-conducting sheet. Non-conducting sheet. And I am saying Q charge is given on this surface, whose area is A. A is the area. Q is the charge which is given. Electric field here is, let us say, E. Okay. Then they will say here is a non-conducting sheet. This is non-conducting. So this one I have to take conducting sheet. Conducting sheet. Here also charge Q is given. Area of this side is A. Okay, students. So they will ask what is the electric field here, E dash. So this is given. So whatever charge is given here, same charge is given here. Whatever area this has, same area this also has. Okay. So they want electric field here in terms of this. This is given. So options will be like this. E dash is E. E dash is sigma, E by 2. Answer should be in terms of E, I told, right? Then E dash will be 2E. And the last option is, as you know, none of this. Now many students think like this. They think, oh, this is non-conducting sheet, so they think this E will be sigma by epsilon naught, which is correct. Actually formula is correct. Sorry, non-conducting is 2 I should write. And this is conducting sheet, so E dash will be sigma by epsilon naught. This is conducting sheet, na? So E dash will be sigma by epsilon naught. So what is the relation between them? You can see cross multiply. Sigma by epsilon naught will be 2E. So I can write 2E. So they will take this option, which is wrong. This is the right answer. Now you think why this is the right answer. I will give you some time. Pause the video and think, how come, Are sir, we thought this is the answer because formula you just now you told us. So think about this, why it is like that. Take some time. Okay. Now I hope you have thought about this. Now you think carefully. If you have found the answer, very good. So now think carefully. They told Q charge is given here, Q charge is given here. Now this is non-conducting sheet. So whatever charge is given on this side will stay on that side only. So what will be sigma here? Sigma here will be Q by A. Okay. So what will be electric field? This is non-conducting sheet. So what is the formula? Sigma by 2 epsilon naught. So it will be Q by A 2 epsilon naught. Fine. Okay. Now this is conducting sheet, students. So when you put charge here, you cannot say it will stay on one side. It will spread on the entire surface. This side also, that side also. In insulator, if you put charge on one side, it will stay localized. It will stay localized. If you take a plastic scale and you do like this, the charge will stay there only. But for conductor, if you do, it will spread on the entire surface. In fact, you are also conductor and you are on ground. Ground is also conductor. So little bit of charge that you are doing here will spread on the entire earth, including you. That's why the spoon, the conducting spoon, never gets charged when you do like this, because the charge keeps running to the ground. Are you clear, students? Okay. So here the sigma will be equal to charge is Q divided by area, not only A, because it is spread here also and back side also. So 2A you have to write. Very, very important point. So charge will spread here also and that side also, because some thickness you have to assume if it is conductor. So some charge will be here, some charge will be here. Okay, students? It is not enough to show just one sheet. So the charge density will be charge divided by area on which it spreads, and it will spread on both the surfaces, this side also, that side also. So that 2 will come. Now what is the formula for electric field near a conducting sheet? Sigma by epsilon naught. Formula remains the same, but when you substitute in terms of charge, it will become how much? Q by 2A epsilon naught. Now check the two formulas. You can see E dash is equal to E. Such a beautiful question, right, students? Okay. In other words, this sigma is different from this sigma. Okay. So keep this in mind. So now let us discuss the topic of electrostatic pressure, which was the main topic for today. So again, to derive this formula, see such a nice technique I am going to use. So let us write the name of the topic, electrostatic pressure. So look carefully. Imagine you have some kind of conductor, any kind of conductor, okay, and it has been charged. Now the charge will not spread uniformly because it is not a sphere. So wherever it is pointed, their charge density will be more. Already I have explained. Now, what is the meaning of electrostatic pressure? Last class, in the last part of the video, I have told you that if you take any part of this conductor, small part of this conductor, other charges will be repelling that part. Each part will be feeling forces from the other parts, and that creates the pressure. Okay. So now let us think of one small part here. Let me color it as red color. Is it visible? I hope so. So let me just darken it more. So I have taken a small part here. Okay. Anywhere you can take. So let us say this part has area dA. Surface area dA. Okay. It's a 3D object. Huh? This is a three-dimensional object. Three-dimensional object. Potato you can think. Potato. But potato is not conductor. So first you coat the potato with gold liquid, okay, molten gold. You will coat it and then make it a conducting sheet. Now listen carefully. So this part has some area dA and some charge, let us say dQ. Okay. So once I know what is the electric field produced by the other parts here, once I know electric field produced by the other parts here, then I can find the force on this part. Yes or no? If you know that a small charge Q naught is present at this point, a small charge Q naught is present at this point, and another charge is producing electric field E, another charge. Same charge cannot produce electric field which will exert force on itself, remember. That never happens. I will produce electric field which will exert force on you. you will produce electric field which will exert force on me. I will not produce electric field which will act on me itself. Okay. So this charge, if you put at some point and if there is electric field at that point due to some other charge, then how do you find the force on that charge? Q naught into E. So many times we have discussed this formula, right? Okay. So basically what I have to do is try to find electric field here due to other part. Okay. So now look carefully. Let me take one point just inside and one point just outside. Okay. So 2 points I have taken. Point number 1 just inside. Point number 2 just outside. Now who will produce electric field at this point? This charge and remaining charge also. Electric field at any point is produced by whatever charges are present. Superposition principle you have to use, remember. So electric field at point 1 will be due to this red part plus due to this remaining part. So let us name them. Let us call EE as electric field, or let me write ES, electric field due to small part. So S here means small part. That way let us create our own symbols, right? And ER is electric field due to, what do you think this R is for? Remaining part. Okay. So now electric field due to this part, since it is positive, it will be away. So this, at this point 1, electric field due to this small part, red part, will be away. Right? So this is your ES. And electric field here due to remaining part will be away that side. Okay, so let me show it here, it's away that side. You understood, no? Everybody understood or no? So electric field at this point due to this small charge. See this small charge here. It's positive, no? So electric field here will be away this way. And remaining part is somewhat like this, positive. So electric field at that same point due to remaining part will be away like that. So these are the two electric fields. And it is obviously they have to be in opposite direction. Can you tell me why they have to be in opposite direction? Because I have chosen a point where? Inside the conductor. And inside the conductor, what is electric field? 0. Please remember that. So these two must be in opposite in direction. Similarly, let me better write with black color. Okay, it will be darker. So one arrow is representing electric field due to small part. One arrow is representing electric field due to remaining part. Similarly, at point number 2, electric field due to this plus charge will be small plus charge will be away. And since these points are just inside and just outside, magnitudes will be same. So this will be E due to small part, ES. And due to remaining part also it will be away. E into remaining part. You understood? No? So if I take point here, then due to this will be away, and due to this also it will be away. Okay? So I hope everybody understood this. Very good. Now once you have understood the directions, you know inside the conductor, what is the electric field inside the conductor? 0. So net electric field inside the conductor is 0. That means this ER minus ES. Why minus? Because these two are in opposite direction. Inside the conductor, these two are in opposite direction. So total will be first vector minus second vector. Because they are in opposite direction, so we have to subtract. So that should be 0. That means the magnitude should be equal. Okay? And this is inside. And outside the conductor, these are just inside and just outside. Okay? Just inside, just outside. What will be the electric field? E net will be this plus this. ER plus ES. Right, students? Okay. But just outside, what is the formula? Let us say sigma here is sigma. Surface charge density is sigma here. local surface charge density, local. So if surface charge density is sigma, then what is the total electric field just outside? Sigma by epsilon naught, already we know. And from here we know ER and ES are same. So I can write ER plus ER using this formula. Right, students? So what will be my formula now? If you look carefully, let me write it here. So sigma by epsilon naught will be 2ER. So ER will be how much? Sigma by 2 epsilon naught. Something wonderful we have done. So electric field due to the remaining part. So let me rub everything now. If you want to write, you can pause and write. So electric field due to remaining part here is how much? So electric field due to remaining part is how much? Sigma by 2 epsilon naught. So let us now go back to the concept of electrostatic pressure, remember. So once we know the formula, so if you remember, we have this kind of conductor and I took a small area here dA and charge on that part I wrote dq, and this is the electric field just outside. Just outside means on the surface also, remember. So this is the electric field just outside, but due to remaining part. So the force on dq charge, see, it is so beautiful, students. So force on this dq charge will be what? dq into electric field due to remaining part. Remember, I have told you, if I want force on you, then I should use your charge into electric field produced by other charges. So charge on, I want force on this charge by other charges. So for that, what I did, I found the electric field just here due to remaining part, which is this. So into E due to remaining part. So this is charge on this part into electric field due to remaining part. And this is sigma by 2 epsilon naught. Sorry. Now dq, how I can write? Since sigma here, local surface charge density. No, matlab surface charge density. What is that? Charge by area. For this part I wrote, what is the charge? dq. Area I wrote dA. So if I use this definition here, what will be my dq? Sigma into dA. And what will be my electric field outside? Sigma by 2 epsilon naught. Not the total electric field outside. Total electric field outside is sigma by epsilon naught. This is due to remaining part. So that F will be equal to sigma squared by 2 epsilon naught. Let us put this area this side. Oh, what is this now? Force per unit area. So this is your electrostatic pressure. Force per unit area is your electrostatic pressure. So this quantity PE, which I am writing, is your electrostatic pressure. And the formula is sigma squared by 2 epsilon naught. Okay. So let us now apply this concept of electrostatic pressure to solve one problem. Okay. So first remember, electrostatic pressure, which is force per unit area on any charged surface. So electrostatic pressure formula is what? Symbol I am writing PE. Formula is sigma square by 2 epsilon naught. Okay, so it has to be charged, otherwise how can sigma be there? Sigma is charge per unit area, right? Okay, so based on this, let us discuss one problem. So this is equilibrium of a charged bubble. Okay, so imagine you have a bubble of radius r. This is a bubble. Okay, now if it is uncharged, then I hope you remember from your first PU concept of the chapter surface tension. So I want all of you to look this chapter, first PU concept surface tension chapter. So there we have taught you that excess pressure, Pi minus Po, pressure inside is always more than outside. and that difference was equals to 4s by r. S is your surface tension, this S. Okay, in some books they write capital T also, but if it is charged, if the same bubble is charged, let's say I put here only charged, then see how the formula will change. Now this surface tension is the property due to which it shrinks the surface, right? Surface tension is the property due to which the surface tries to minimize its area. Please remember that, otherwise let me know, I will revise it. So surface tension is the property of a liquid surface due to which it tries to minimize the area. So due to this surface tension, the pressure tries to increase. Okay, that's why Pi minus Po is this. Pi is greater than Po. Okay. Now since it is charged, you know that there will be outside pressure like this. There will be pressure which will try to expand the bubble, and that pressure is your electrostatic pressure, sigma square by 2 epsilon naught. So excess pressure now will be, this is trying to shrink the area, surface area. This is trying to increase the area. So I should write minus electrostatic pressure, sigma square by 2 epsilon naught. So keep this formula in mind. Okay. So if it is charged bubble, you have to include this formula also. And why minus? Because surface tension, whatever charge is doing, is opposite to what surface tension is trying to do. Surface tension tries to minimize the area. The charge on the bubble, whether you give positive or negative, it doesn't matter. Like charges will repel each other. So the electrostatic pressure will try to blow the surface. This will try to shrink the surface. So excess pressure will be reduced because of this pressure. Okay, students. Now in some questions, they may mention pressure inside is equal to outside. If they mention this, then what will happen? Then this will be 0, this will be 0, so you will get 4s by r equals to sigma square by 2 epsilon naught. So from here, they can ask you radius, they can ask you surface tension, they can ask you surface charge density. Any question can be made from this concept. So I hope everybody understood this. So let us now solve question number 55 and 56 for JEE. Okay, these are the two questions pending. JEE 56 first. To do this problem, first let us do another concept called self-energy. Self-energy, or sometimes it is called potential energy only, of a shell of charge. Shell of charge. Okay, so what this means is, imagine I have a shell of radius r and charges will be on the surface, right? Okay, so what I am doing is, this has total charge capital Q. So I want to know what is the energy of this shell. It will have, because what is the definition of potential energy of multiple point charges? So when there are many charges, what is the meaning of potential energy of a system? See the definition. It is the work done to bring the charges from infinity to their respective positions in the system. So if you remember, I have done derivations also. So all these charges which are sitting on this shell, okay, will have potential energy, because this is a system of charges only, right? And system of charges will have potential energy. That potential energy is also called self energy. So what will be the energy of this shell? Let us try to find. So to find the energy of this shell, listen carefully. What we will do is, first let us assume I have no charge on this shell. Okay. So then I bring dq charge. So what I am going to do is, I am going to calculate work done to bring all these charges which were there, capital Q, from infinity to their positions. So first what I will do, I will put dq charge here. Bit by bit we will do, bit by bit. So first I will put dq charge, and this dq charge will spread on the entire surface. Okay, so this is the dq charge. So then I will put another dq, then another dq. So at some instant, let us say the charge here is q. So at that instant, what will be the potential on the surface? 1 by 4 pi epsilon naught q by r. Correct na? So this is the potential on the surface of the shell right now. Now when you will bring another dq charge from infinity to this surface, what will be the work done? Q into potential. Just now I have told you, from A to B, if you bring any charge, then what is the work done? Q into VB minus VA, right? From infinity if you bring, then this will be your infinity. But potential at infinity is 0. So work done from infinity to B will be simply charge into potential at B. So you know that at every point potential is same, right? So whatever dq you are bringing from infinity and spreading it on the surface, you have to do this much work, sorry, dq. So dq amount of charge you are bringing from infinity against the forces of those charges which are already present. So the work done will be dq into potential. This is dw because the charge which we are bringing is small charge, so work done also will be small. Now what is dq? dq is just dq. What is potential? 1 by 4 pi epsilon naught q by capital R. So this much work is done to bring dq charge from infinity to the surface of the shell, when there is already how much charge present on the shell? Q charge. If there was no charge present, then no work has to be done. I hope you are understanding, right? Remember how we found work, potential energy of 3 charge system, q1, q2, q3, like that. So first I took all of them to infinity, then I brought first q1. I calculated the work. That time it was free of cost because there was no charges. Then when I brought q2, I had to do work against the force of this charge. And how I wrote that work? q2 into potential produced by q1. Then when I brought q3, I had to do more work because when I bring q3, two charges will be sitting already. So more force q3 will feel. So I have to do more work against two forces now. Understanding? So this is how I derive the formula. Please check that derivation first. So similarly, this charge on the shell. So here is the shell. Total charge is capital Q. They have told. I have to find energy of this shell. So this capital Q also must have been brought from infinity to this surface. So I can divide this capital Q into many dq's, dq, 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 like that. So to bring each dq, how much work I have to do? Just integrate, just add. But you cannot just directly multiply this q into v. That is because the work is the force acting on these dq charges are variable. Initially you will feel less force, later you will feel more force, more charges will come here. So later when you will bring first dq, when you will bring, that time you will be able to bring it free of cost, first dq, because this is uncharged right now, no? So when I bring the first dq, it will be very easy. Then when I bring the second dq, I will have to do work against the first dq. Then when I bring third dq, then I will have to do more work. So the force acting on the charges which you are bringing from infinity to this shell is changing all the time. Therefore, you cannot directly multiply charge with voltage or potential. You have to use integration. So first what I did, I calculated work done to bring dq charge when already q charge is sitting here. Okay, so this q charge is already sitting here. This is the work done to bring dq charge against the force of this q charge. And how do I do that? Just multiply dq with potential, because that is the definition of work done to bring dq charge from infinity to some point. Here the point is basically the surface of the shell. Why? Because every point is at same potential, it doesn't matter. Okay, so this is the small work done. Now total work done to bring capital Q charge on this shell, starting from what charge? Initially what was the charge? 0. That will be 0 to capital Q. You have to integrate. So if you integrate this 0 to capital Q, see what will you get. So that work done is basically the energy stored in the shell. Okay. So constants you can take outside, right? So work done will be constants you take outside. 1 by 4 pi epsilon naught r will come outside. Integral q dq from 0 to capital Q. So that will be equal to 1 by 4 pi epsilon naught r. Integration of x dx is x square by 2. So this will be q square by 2. Upper limit capital Q, lower limit 0. So this will be put upper limit 1 by 4 pi epsilon naught capital Q square by 2, that will make this 8. So it will be 8 pi epsilon naught r. Okay, so finally let me write properly. This is the work done. Complete work done to charge the shell from 0 to capital Q. 0 to capital Q. Okay, students. So here, instead of using force into displacement formula, I am using charge into potential formula. That is easier because potential we know already due to a shell. So what is the potential energy stored in the shell? Whatever work you have done to charge the shell from 0 to capital Q, right? It has 0 charge, now it has capital Q charge. And what is the meaning of potential energy? The work done to bring these charges from infinity to the surface of the shell. So what is the answer? Q square by 8 pi epsilon naught r. So whatever work you do is the energy stored in the shell. So this is the energy stored in the shell. Okay. Now listen carefully. If I give you conducting sphere, this is conductor. Now it may be hollow, it may not be hollow, it doesn't matter. The reason is, if you put charge on a conductor, it will stay only on the outer surface. So for this, if I ask the energy stored, then the answer will be same. Why it will be same? Because just like a shell, even here the charge is only on the outer surface if it is conducting sphere. Okay, you try for homework, you try for a system which has solid sphere everywhere, solid charge. So the sphere has charge everywhere inside. So think of this as a insulating charged sphere. This will be more difficult, but you can try. You can find this in the book B.M. Sharma, okay? Cengage publication. So those who are interested in advanced problems, you can try to find potential energy of a charged solid sphere which is not conducting. If it is conducting, then the charge will stay on the outer surface, so it will be like a shell only. So this formula we need to solve question number 56. Later, when I will do capacitor chapter, this formula can be derived more easily. Here we did lot of integration, that will be not needed. Okay. So see question number 55. A solid conducting sphere of radius 10 cm is enclosed by a thin metallic shell of radius 20 cm. Let's draw a diagram. Solid conducting sphere is enclosed by a thin metallic shell. This has radius 10 cm. This has radius 20 cm. Okay. A charge Q equal to 20 microcoulomb is given to the inner sphere. 20 microcoulomb is given to the inner sphere. Find the heat generated in the process if the inner sphere is connected to the shell by a conducting wire. So if you connect a conducting wire, what will be the heat generated they are asking. Now why they are asking like this? Let us think. So right now, before connecting the wire, what is the energy stored? Energy stored, let us calculate. U initial. Now here there is no charge given. Okay, so no energy will be stored here. And even if induction will happen, minus Q plus Q, total charge is just 0 only. So this will have negative energy, this will have positive energy. They will, when you add, they will cancel. So no need to worry about induction. So the charge is only on this sphere, right? So since it is conductor, the charge will stay on the outer surface. So I can use the formula for shell. So energy stored will be 1 by 4 pi epsilon, 8 it was, 8 Q square by radius. Okay, so this Q is your 20 microcoulomb. So let me write this as 4 pi epsilon naught only and this as 2r. Okay, that way it is better, right? Now 1 by 4 pi epsilon naught is what? 9 into 10 power 9. Initially, what is the charge? 20 microcoulomb they told, right? So 20 into 20, 10 power minus 6 square will be 10 power minus 12 divided by 2 into radius. Radius of this inner sphere is 10 centimeter. So 10 into 10 power minus 2. 1 0 1 0 you can cancel. 1 2 1 2 you can cancel. So 9 2s will be 18 into 10 to the power how much? 9. This will be 10, right? 1 10 to the, this will be 10 to the power 1, no? So 10 power 1, 10 power 9 will be 10 power 10. Then minus 2 will come up plus 2. So 10 power 12. 10 power 12, 10 power minus 12 will be 10 power 0. So it will be 10 power 0. So 18 joules. So right now 18 joules is stored in this system. Okay, students? Okay. Now once you connect a wire, they told, what will happen? Already we have discussed today. So once you put a wire, the whole charge will go here. Okay, so now the final energy stored. This is initial energy stored. So final energy stored. Final energy stored. U final. Same formula, we can use the same formula, but look here. Radius of this is double of this. So this radius will be double. This R I have to replace it. Here I wrote R how much? 10. No. Now I have to write 20. So 1, 2 will come in the denominator. Okay, so try to do yourself. I hope you understood. Everything is same. Q is same C. Now the only difference is now the charge is not in this shell. It is in this shell. Okay. So all the charge will go there. So energy stored will be now. Formula will be same, but radius now will be 20. So here if I write 20, 2 will be there, one extra. So divided by 2 in the denominator it will be there. So if you divide by 2, you will get 9 joules. Now you will think, initially it was 18 joules. Now it is 9 joules. Where did the energy go? So some energy is lost. So the energy lost is what is going into the heat. And the heat energy lost or heat produced, the heat released is the energy lost. And that will be your initial energy stored minus final energy stored. That will be 9 joules. So that is the answer. Now some of you may be thinking how some heat is produced. See, when this charge is going to the outer shell, there will be current for some time, current. And current topic I will be teaching the next chapter. So when there is current in a wire, no, always heat is produced, right? That is how immersion rods, they work, right? So immersion rods will have some filament. So when you connect it to the power supply, current flows in the filament and it gets heated. So when you put it in water, the water gets heated. Or you take bulb for example. When the bulb is used for some time and you touch it, it gets hot. Okay, so current flowing in wire always results in heat. And why current is flowing? Why there is current? Because these charges will be going to this sphere, no? So during, for some interval, there will be current, and that current is what is resulting in the heat. And how much energy is lost? 9 joules. So I hope everybody understood. Again, beautiful question, provided you know this formula. Okay, let us do the last question now. 57. To do this question, okay, another concept. One concept you need is electrostatic pressure, which already you know. But this another concept which is quite useful is this. Look here. Suppose I have a area like this here A, and force is acting like this. Force. Then the pressure is force per area. So force will be pressure into area. But if the surface is like this and forces are acting like this, then we don't talk about pressure. Then the force on here, the pressure is basically 0. Okay, pressure, even if pressure is not 0, force will be 0 due to pressure, because you need area perpendicular to the force. Force is not 0 actually, sorry, pressure is not 0. Every point there will be some pressure. Understood or not? But there will be no force on this surface, because the force due to pressure is always perpendicular to the surface. That's why we call this force thrust also. If you see your first PU notes where we have discussed pressure for the first time, we have called this force as thrust. Thrust here means perpendicular to the surface. So if it is parallel to the surface, then there is no force due to the pressure. Okay students, on this surface. It may be there on this surface, no doubt. But on that surface, it will not be there. So it is very important that the area is perpendicular to the direction of force. So if molecules are coming and hitting like this on my surface, then there is a force due to the pressure. But if they are going like this, then there is there's really no force due to the pressure. My skin is not going to get pressed. Are you understanding if they go like this? So I hope you understood this concept. Now in some cases what may happen is this. The area may be slant like this, okay? Like this. So let me try to show it more properly. So let me try to show you 3D way, okay? Yeah. So suppose the force is acting this way. On this surface. So you can think molecules are coming and hitting this way. Now, if you want to find the force due to the pressure on this surface, you should not use this area. You should use the area which is perpendicular to the surface. So you should use component. So if this area is A and this angle is, let's say, theta, you can say this also theta, your wish. And if this area is A, you have to project this area. So this is the area right now. You have to project it perpendicular to the surface. So you have to use, to calculate the force due to pressure, you have to use pressure into area which is perpendicular to the force. So if the area is already perpendicular, then no problem, use A. But if it is that, if area is at angle, then you have to project the area. Project the area means take component of this area perpendicular to the force. And what will be the area per a component of this area perpendicular to the force? It will be this backside area. Yes or no? That area is what? Perpendicular to this force, and it is component of this area only, right? You can think of this area is, you are understanding or not, students? So this area, how will I calculate? Well, if this is A, then this backside area will be A cos theta. Okay, so here while calculating the force, I should write P into A cos theta. So I hope everybody understood. If you are thinking how this area is A cos theta, look carefully. Let me teach you another way. Okay, so let us say this is breadth and this is L, this is L dash, this is theta. Now what will be area of this rectangle? This slant one. This area will be length into breadth, no problem. Right? It's a rectangle, no? Yes or no? This is the length, this is the breadth. For this backside area, backside, okay, what will be area? That is the area which will be length is L dash into breadth. Now try to connect L with L dash. You can connect it by using cos theta formula. So adjacent is L dash, hypotenuse is L. So in place of L dash, I can write cross multiply. Hypotenuse is L, no? So in place of L dash, if you cross multiply, I can write L cos theta into B. But what is L into B? L into B is this slant area, So this is how I am saying that the area which is perpendicular to this force is A cos theta. Even if this area is A, you cannot use this area while calculating the force due to pressure. You have to use the area which is perpendicular to the force. Okay, students? So I hope you understood now that if this area is given as A, then you have to use this area. And this area is called projected area. Projected means this is the area. If you project it perpendicular to the surface, you will get this area, which will be smaller than this because it is component of this area. No, component should be smaller only, but it is perpendicular component. So I hope you understood how to find the force due to pressure when the area is not perpendicular to the force. So similarly, think there is a hemisphere, okay, not semicircle, hemisphere, and the force is coming like this, okay. This radius is r, let's say. So the force is in this direction. So to find the force in terms of pressure, you put pressure into area which is perpendicular. Now the given area is this. The surface where the force is acting is like this. So now you project this area perpendicular to the force. You will get this area. Understanding or not? So if you take this curved area of a hemisphere, and project it perpendicular to this force, you will get this circular area. I hope you understood, and therefore I can write simply P into pi. This area is circular area, no? So I can write pi r square. So keep this very important in mind, okay? So having understood all these small concepts which are important for your problem solving, let us see now the last question number 56. A uniformly charged thin spherical shell of radius capital R carries uniform surface charge density of sigma per unit area. So there is a uniformly charged shell like this. It is charged. Since it is sphere, the charge will distribute uniformly. Then the radius is r and sigma is the surface charge density. It is made up of two hemispherical shells. So you can divide this into two hemispheres. One hemisphere here, one hemisphere here. Held together by pressing them with force F. So they want you to find force is proportional to what? So they want how much force is needed on each side to keep these hemispheres together. If you don't apply this force, then what will happen? Already we know each part of this is feeling a hydrostatic pressure because of, sorry, not hydrostatic, electrostatic pressure, because of which they want to go away. So you are needing some force, you need some force to balance this outward force due to the electrostatic pressure. So we have to find this force, or you can say this force, your wish. Now, what is the pressure on any part? So we are interested on this hemisphere, no? So let's take one of the hemisphere. Now, the force due to the electrostatic pressure will be what? Force due to electrostatic pressure. Remember, we are calculating force due to pressure only. So that will be equal to electrostatic pressure into area which is perpendicular to this force. Now, the surface may be curved, but I should use only the what area I told, projected area. So this is the projected area. Okay, students? So net force will be this way. See, forces may be acting this way, actual forces. But when you resolve all these forces, you will get net force in this direction, right? This force and this force will add to give you this force only. Resultant force will be here only. So resultant force on this hemisphere will be this way. Now the surface is curved. So you don't have to use the actual area. What you have to do, project the area perpendicular to the direction of the electrostatic force. Okay, and that projection of this area perpendicular to this force will be this area. So this is your A perpendicular, which will be what? Pi r square. Right, students? So what is the formula for electrostatic pressure? Sigma squared by 2 epsilon naught. And what is the projected area? Pi r square. So this is the electrostatic force on one hemisphere. Now if there is no forces to balance this, it will just fly apart. So you need to apply some external force F, they told. So to balance this, what you have to do, your external force should balance this electrostatic force to balance. Okay, so what is the electrostatic force? Sigma squared by 2 epsilon naught pi r square. So that much force you also have to apply. So it is proportional to what? Sigma square into r square. So option A is the right answer. There is no point writing epsilon naught. Okay, since they are saying proportional, so we should write variables only. But I have given you the force only, right, directly. So I hope all of you understood this concept, students. So this is very important. Okay, again I am telling you, if your area is like this, slant, okay, think of this as the area, this. So if I keep it like this, okay, like this, so I am showing you only this line. Then the force is acting on this area like this. Then the force due to pressure, okay, then the force while calculating, you have to multiply pressure with not this area. You have to use the component of this area perpendicular to the force, like this. Okay, so this area you have to use. So in 2D it will look like this. In 3D it will look like the one I was explaining to you, right? Like this. So you have, even if the area may be like this, okay, and the force is acting like this, you have to project this area perpendicular to the force. Now if you think of this way, so think you have this kind of area and the force is acting like this, then you have to project this area perpendicular will be this one, no need to project. If you project also it will be same, no. And for this area, if you project it perpendicular, you will get this. So that is how I am saying this part. So for this area, the projected area will be this. Understood, students? So if you think in 3D, for this area, this is the projected area. For this area, no need to project. Same thing is the perpendicular. For this area, you have to project it perpendicular to the force. So for this hemisphere, when you project it perpendicular to the force, you will get this circle. So don't use the actual surface area, you have to use only the area perpendicular. That is because, see, this one will have one component here, one component here. And this component is useless to find the force due to the pressure because it is parallel to the surface. So if the force is parallel to the surface, there is no pressure on the surface. Okay, so I hope you all understood this concept. Try to revise whatever I have done, and very good questions we have done today. So I hope with this you will be able to score more marks in your entrance exams. I am seeing your performances in PTEs. So those students who were not doing very good last year are doing very good this year. So I'm very happy for them. And some students who were doing very good are not doing very good this year. So please try to buck up, okay? Try to get excited and be more interested towards whatever is going on in studies. Physics is very, very interesting, okay? It can, the point is you have to know the concepts very well. And to know the concepts, you have to have a good teacher and you need to read good books. So if you have that, it will be, and you need to also keep asking as many doubts as possible so that all your misconceptions are cleared. Okay, so with this we'll stop this class, and I think from next time the classes will be online live classes it will be, so you will get opportunity to ask directly. Like right now, see, when I'm explaining, sometimes I explain too much also because I'm not able to gauge. I don't have students in front of me to see their eyes and to know whether they have really understood or not. So sometimes I may explain more than required, but I hope you all will still feel happy that you have understood. Okay, so with this we'll stop. Thank you. Have a good day.